You sit down at your keyboard, you type a mind-bendingly complex math problem or a highly specific coding prompt into one of the newest generative AI models, and you wait.
Yeah, the waiting is the key part.
Right. You've probably noticed this recently. There is this distinct pause. The AI seems to take a few seconds to actually, think before it starts generating tokens. And it's not just loading or like dealing with server latency. I mean, it is actively performing massive calculations under the hood before it spits out this brilliant, flawless proof.
And that pause, really, is the frontier of modern machine learning.
Hmm.
Because for a long time, we were all conditioned to expect instantaneous, almost reflexive, autoregressive text generation.
Exactly. You hit enter and the text just flies across the screen.
Right. You feed an input into a transformer, and it just immediately starts predicting the next token.
Uh-huh.
But when you move from writing emails to solving, say, open mathematical conjectures,
Yeah.
that purely reflexive approach just collapses entirely.
Which brings us to our focus today. We are doing a deep dive into a really fascinating state-of-the-art research paper from June 11th, 2026. It's titled The Power of Test Time Training for Approximate Sampling.
Oh, this paper is a game changer.
It really is. It's authored by Noah Golowich, Onkar Moitra, and Dhruv Rahatgi. And our mission in this deep dive is to unpack this highly technical paper and translate its dense mathematical proofs into a clear understanding of why this concept, test time training, is completely revolutionizing AI.
It's a huge shift in how we approach sampling.
Definitely. Okay, let's unpack this. Before we get to the big breakthrough, I think we really need to define the bottleneck.
Good idea.
Why does a standard, autoregressive large language model struggle so much when it tries to generate a specific mathematically rigorous proof?
Well, it really comes down to the difference between generating plausible text and generating logically flawless sequences.
Right. Plausible versus flawless.
Exactly. In machine learning, efficiently sampling from a really complex probability distribution is just a fundamental challenge. And the industry standard setup for this usually relies on two components.
Okay, walk us through them.
So first, you have your base model. This is the reference model, which mathematically they denote as PyRef.
So that's just your standard LLM, right? Trained on vast amounts of internet data.
Yep, exactly. And second, you have a reward model, specifically a process reward model, or PRM, which the paper denotes as VHAT.
Right. And in a typical setup, the workflow there is iterative, isn't it? Like the base model generates a sequence of tokens, say the first three steps of a complex geometric proof.
Yes.
And then the PRM evaluates the intermediate state. It acts as like a value function, scoring the log probabilities to decide, if that partial text is actually on the right track.
Exactly. The idea is to use those scores from the PRM to guide the final generation toward the target distribution, which in this case would be the perfect mathematical answer.
That makes sense in theory. But wait, so if we already have a reward model acting as a teacher, like grading the AI's work step by step, why is the AI still struggling? Shouldn't it just follow the good grades?
Well, what's fascinating here is that the base model can only propose solutions based on its inherent training distribution.
Right.
So if that underlying training makes it naturally prone to suggesting terrible approaches to, say, a niche combinatorics conjecture,
Oh, I see.
the PRM will just repeatedly assign it low-scalar rewards. The model is essentially just guessing, getting penalized, and then trying another blind guess from that exact same flawed starting distribution.
Let me jump in there because I know a lot of our listeners who work with reinforcement learning or like search algorithms are going to ask, if we have a PRM acting as a value function, why can't we just use Monte Carlo pre-search or beam search?
Yep.
You generate multiple branches, the PRM scores them, and you just aggressively prune the tree and follow the high scores. Why is that still failing?
Because of the massive distance between the distributions.
What do you mean?
Well, if the base model's natural output is just too far away from the desired target distribution, the search space becomes exponentially vast. You aren't just searching for a needle in a haystack.
Okay.
You are searching for a needle in a haystack where your search algorithm naturally prefers to only look at pieces of hay.
Wow.
Yeah, so the number of queries back and forth between the base model guessing and the reward model evaluating becomes prohibitively huge.
So we are just burning massive amounts of compute, generating bad ideas just to get them rejected. I mean, you might eventually find the right path, but the computational cost of evaluating all those dead ends makes it, like, completely impractical for real-world application.
Precisely. And the authors point out that this isn't merely a practical frustration of modern LLMs.
No.
No, it is deeply tied to a classic theoretical computer science problem dating all the way back to the 1980s.
Oh, wow. Really?
Yeah, the struggle these massive neural networks face today when sampling is actually an echo of a mathematical limitation established over 3 decades ago.
Okay, let's trace that lineage. We're talking about a time long before anyone was even conceptualizing, billion parameter transformer models.
Exactly. We have to look at the seminal works of Jerome, Valiant, and Vazirani back in 1986.
Okay.
And then Jerome and Sinclair in 1989. These researchers were really focused on the algorithmic equivalence of sampling and approximate counting.
Which means what, in layman's terms?
Well, in combinatorial spaces, counting the number of valid solutions to a problem is often equivalent to the difficulty of sampling one of those solutions uniformly at random.
Right, okay.
They proved that you could approximately sample from a complex target distribution by doing a random walk, specifically a Markov chain Monte Carlo approach.
Let's ground that for the audience real quick. A random walk in algorithmic space means the system basically transitions from one state to another, right? Just exploring a massive tree of possibilities.
Exactly.
And it uses an approximate counting oracle, which is just a mechanism that can estimate the number of valid paths ahead to guide its steps. And when it realizes it made a mistake, it backtracks.
Yes, that backtracking is the key. But exploring a state space that way takes time, a lot of time.
Right.
Which brings us to a huge open question posed in 2010 by Hayes and Sinclair. They basically asked, is it possible to approximately sample from a target distribution using fewer than a quadratic number of queries?
Okay, let's clarify that. In algorithmic terms, can we do it in little o of n squared time?
Yes, exactly, where n is the length of the generated sequence.
To visualize n squared for you listening, if you are generating a highly technical response that is 1,000 tokens long, the number of queries required to navigate that random walk would be proportional to 1,000,000.
Exactly. 1,000,000.
If you need 1,000,000 passes through a massive neural network just to generate one coherent output, your compute costs are going to bankrupt you.
Oh, immediately.
So did Hayes and Sinclair get their answer?
They did. And it's actually the paper's first major finding, which they formalize as Theorem 1.1.
And what's the verdict?
The answer is a definitive no.
Wow.
Right. The paper proves mathematically that the Jerome-Sinclair algorithm from 1989 is basically optimal. You absolutely require quadratic time, specifically omega, of n squared over log squared inquiries to sample from the target distribution.
Assuming you are not updating the model itself, right?
Yes. That is the critical caveat. If you don't change the model, you cannot cheat this math.
So what does this all mean? It's like navigating a massive maze blindfolded, right?
Yeah, that's a great way to think about it.
You're only relying on a friend shouting warmer or colder. And the paper proves there is a fundamental, strict mathematical speed limit to how fast you can find the center using just that method. You're paying a really heavy tax on every single step you take.
Precisely. If you hold the base model fixed, meaning its parameters and its internal weights are totally frozen,
Right.
and you rely entirely on filtering its outputs through a reward model, you're paying that tax. No matter how clever your pathfinding algorithm is, whether it's Monte Carlo tree search or some advanced beam search, you will inevitably hit that quadratic speed limit.
You are mathematically doomed to be slow.
As long as the model is static, yes.
But we know that isn't the end of the story. I mean, we've seen the headlines. The paper explicitly mentions systems like AlphaProof achieving silver-level performance at the International Mathematical Olympiad.
Exactly.
You do not get an AI to solve IMO problems if it requires an infinite amount of compute to bypass a quadratic bottleneck. They are obviously breaking the rules somehow.
Well, they aren't breaking the rules. They're completely changing the paradigm.
Okay, explain.
This is the transition to the core solution of the paper, test time training, or TTT.
TTT, right.
Instead of holding the base model fixed and just filtering its outputs, test time training actively updates the model's parameters, its actual weights, during inference.
Wait, during inference, in response to the reward feedback.
Exactly. On the fly.
Okay, I have to push back hard on this because retraining a neural network on the fly sounds like a complete computational nightmare.
It does sound crazy at first.
Right, because we know that updating weights requires gradient descent. That is the backward pass, which is traditionally reserved for the initial training phase, the stuff that takes massive server farms months to complete.
Yes.
So if our bottleneck is already that generating tokens takes too much time. How does doing massive amounts of calculus to rewrite the model's brain during the test actually speed up the sampling process? I mean, that sounds like you're adding a massive overhead.
It sounds completely counterintuitive, I agree. You're trying to solve a speed issue by adding an entire learning step.
Exactly.
But the paper addresses this by establishing a really rigorous theoretical framework. They mathematically formalize test time training, not as some chaotic, unconstrained tweaking of a billion parameters.
Okay, so what is it then?
They define it as an operation within a boundary. TTT relies on a promise that the perfect target distribution belongs to a known bounded class of distributions. And they denote this mathematically as script F.
Script F. So the model isn't just searching an infinite parameter space for a solution. It has this predefined structural boundary.
Exactly. It acts as a really powerful inductive bias. By knowing that the solution definitely lies somewhere within this specific class of distributions, script-F, the AI basically gets a structural clue about where to look and how to adapt.
Oh, I see. I think an analogy will really help our listeners here.
Go for it.
So if standard sampling is like exploring a pitch black room by feeling the walls, hitting a dead end, and backing up, which is the random order, test time training is entirely different. With TTT, every time you hit a wall, you basically rewrite your brain's actual floor plan. You update your internal weights so that that specific dead end effectively ceases to exist in your probability distribution.
Yes. You physically cannot imagine walking that way again.
And because you are operating within script.f, you understand the general architecture of the building, meaning you can infer where other walls probably are without having to physically walk into them.
That captures the dynamic perfectly. You are shifting the base distribution so it aligns closer and closer to the actual target distribution.
Wow.
And because TTT restricts the search space using this class script F, we arrive at the paper's second major finding.
Okay.
This is where they actually shatter that historical quadratic speed limit.
This is theorem 1.2, right? The subquadratic breakthrough.
Yes. The authors prove that if the size of that known class, script F, isn't excessively massive, you can completely circumvent the omega of n squared lower bound from the 1980s.
That is huge.
It is. The query complexity drops drastically to subquadratic time. Specifically, it drops to big O of n times the square root of the log of the size of script F.
Let's break down that equation for the audience because it's important. Big O of n times the square root of the log of the size of script F.
Right.
What this means mechanically is that the time it takes to sample a correct answer now grows almost linearly with the length of the sequence, the none of variable, rather than compounding exponentially as n squared.
Exactly.
It is multiplied only by the square root of the log of the size of our bounded class script F. That is just an astonishing leap in efficiency. But how exactly are the algorithms executing this under the hood?
So the authors lay this out through two specific procedures. Algorithm 2, which is tree-structured rejection sampling, and algorithm 3, which they term particle filtering with learning.
Okay, algorithm 2 and 3.
Right. And while they operate slightly differently, a crucial shared mechanism between them is the truncation step.
Let's dig into the truncation step because to me, this is where the algorithmic rubber really meets the road.
Oh, absolutely. In a standard setup, if an AI is generating a flawed sequence of math steps, it frequently generates a long chain of tokens before the PRM evaluates the full context and rejects it.
Right, which is just wasted compute.
Exactly.
Yeah.
But in algorithm 2 and 3, the truncation step actively intervenes. As the AI generates a sequence, it continually compares the probability of that sequence against the mean density of the current class of distributions. If the algorithm calculates that the odds of this specific path being accepted by the final target distribution are just infinitesimally small, it prematurely kills the sequence.
It just cuts it off.
Yes, it truncates it immediately.
So if you are listening to this, sitting at your computer, staring at that blinking cursor while the model says it is thinking, this truncation step is exactly what is happening in those empty seconds.
Exactly right.
The model is silently spinning up dozens of partial paths, mathematically proving to itself that they are going nowhere by comparing them to the mean density of class script F and then killing them off before you ever even have to read them.
It aggressively prunes the search tree. However, if we connect this to the bigger picture, this introduces a massive statistical risk.
Really? What kind of risk?
Well, when you start selectively killing off paths and then updating your model's weights based on that pruning, you really risk introducing bias.
Oh, like an algorithmic echo chamber.
Exactly. If the model learns from its own biased sampling, it can easily spiral. It starts amplifying its own bad habits and drifts entirely away from the correct mathematical logic.
Right, because if you only ever explore paths that look good to a flawed model, and you reinforce those paths, you might lock yourself out of the actual correct solution just because it initially looked unorthodox.
Yeah.
So how do they prevent that? How do they stop the echo chamber?
The unbiasedness is maintained through strict importance weighting corrections. This is a super vital part of algorithm 3, particle filtering with learning.
Let's explain how that weighting works mechanically.
Okay, so when you prune a large portion of the search tree, you alter the overall probability mass of your distribution.
Right.
Importance weighting basically corrects this by reweighting the branches that actually survive. Imagine you have a proposal distribution that you have actively shifted away from the original base model.
Right, following you.
To ensure your final output is a true, unbiased sample of the target distribution, you multiply the output by the ratio of the target probability to the proposal probability.
Okay, so to put it simply, if the model learns a path is bad and updates its weights to avoid it, it artificially inflates the statistical value of the paths it does decide to take.
Yes, it mathematically compensates for the pruning.
This ensures that even though the model's internal weights are rapidly shifting and warping to avoid dead ends, the final mathematical output remains perfectly balanced, perfectly mathematically rigorous.
That balance is everything here. The expected number of times a correct sequence appears in the final output perfectly matches the true target distribution, even though the base distribution has radically changed over time.
That's brilliant.
Because the model is constantly updating its reference class script -f based on what it learns, it is dynamically burning the map of bad territories.
Burning the map as it walks. I love that.
Right. It learns the structure of the dead ends, performs a gradient update to reflect that new reality, and literally never wastes time checking those dead ends again.
So it fundamentally changes its own nature during the forward pass to become a model that is natively good at the specific problem it was just asked to solve.
Exactly.
Every time it hits a bad ratio and truncates a path, the algorithm essentially halves the number of distributions in the class script -f that it needs to consider.
Yeah.
The search space just collapses rapidly around the correct answer, which is why that quadratic speed limit is shattered.
And they proved it rigorously. Theorem 1.1 proves the wall exists for any static model, and Theorem 1.2 proves how test-time training, through this dynamic map burning and importance weighting, lets you mathematically bypass it.
This brings us back to why this paper is just so critical for the trajectory of artificial intelligence.
It really is.
We are asking models to verify incredibly complex software systems, right? To design new molecular structures for drugs, to solve combinatorics problems that human mathematicians have been stuck on for decades. We literally cannot wait for 1,000,000 queries to process a single 1,000-token answer.
No, we'd be waiting forever.
Exactly. So the pause you see on your screen now is literally the sound of the AI actively utilizing test-time training. It is updating its neural pathways on the fly, performing importance-weighted pruning, and evolving to meet the specific complexity of your prompt.
It is a profound shift in methodology. But as with all groundbreaking theoretical research, we do have to look at the author's own caveats.
There's always a catch.
There is. In their discussion in future work section, they outline a major hurdle that still remains.
Okay, what is it?
This raises an important question. The paper definitively solves the query efficiency problem, right? We know we need fewer queries, but we still have a computational efficiency problem.
This circles back to my earlier pushback, doesn't it? About the sheer cost of running gradient descent during inference.
It does. The paper proves we don't need 1,000,000 queries. But what is the raw computational cost of the queries we do make?
Right.
To execute algorithm 3 and perfectly track that bounded class of distributions script F, the current math requires explicit enumeration over the entire class.
Wait, explicit enumeration?
Yes. The algorithm has to hold, calculate, and update the mean of all those complex distributions simultaneously to ensure the importance weighting corrections are actually flawless.
Oh, man. So they proved that the door's unlocked, but the handle is currently made of solid lead.
That's a great way to put it.
In theory, the query bound is totally broken. But in practice, explicitly enumerating script F for a massive multi-billion parameter neural network, I mean, that would require an immense amount of processing power just to manage the learning step itself.
It highlights the massive gap between theoretical computer science and applied engineering. The foundational math of the 1980s has been overcome in theory.
But practice.
Exactly. The question for the field now is, who will be the first to translate these structural pruning techniques into a practically fast, Oracle-efficient algorithm.
For our listeners, an Oracle-efficient algorithm basically means we find a way to approximate that scriptf class without having to explicitly map out every single distribution inside it, right?
Correct. We need an algorithm that doesn't require infinite compute to F the reward model if a step is right.
Finding a way to perform this subquadratic, map-burning intelligence efficiently on everyday hardware. I mean, that is the next great race in AI.
It absolutely is.
And that is a really fascinating thought to leave you with. Whoever solves that computational bottleneck, whoever figures out how to approximate scriptf without explicitly enumerating it, they won't just have built a smarter AI.
No, it's bigger than that.
They will have engineered an intelligence that fundamentally gets smarter the longer you allow it to think, without requiring a massive supercomputer to do it. We used to try to navigate algorithmic space by just giving the model a better search algorithm. Now we're giving it the ability to redraw the walls of the maze while it's standing inside it, and that truly changes everything.